So in this chapter, we will introduce differential analysis of fluid flows. So already in the previous chapter, we consider conservation of mass, continuity equation, conservation of energy for a certain control volume. Okay. Now it's similar if you want in as a concept, but now instead of applying to a big control volume on a macro scale, will apply now on a micro scale. So the only difference now is that the control volume of interest will be very small. Okay. So in this case, we say that we will deal with a conservation equations in differential form. Okay. To start with, if you want to apply conservation of mass on the micro scale, we still apply the same relations that we have seen before, which is that the transient variation of mass in the control volume, which represents accumulation of mass or loss of mass, plus sum of m dot out, representing all fluxes getting out of the control volume, minus sum of m dot n equals to 0. Okay? So now, for example, if we consider the following elementary volume of dimensions dx, dy, and dz, we can consider that the elementary volume dv is then equal to dx times dy times dz. Okay? And fluxes of mass can happen on any phase. So you can have here, for example, if you have this phase is in plane YZ. Okay? So we know that when we have a phase, to have a mass flow rate, we should have a component of velocity perpendicular to the phase. So if you have phase YZ, only a velocity component along U can cross the surface. Because if you have velocities along V, along Y or Z, so if you have V velocity or W velocity, they cannot cross YZ phase. Okay? So to cross a phase, the velocity should be perpendicular to the phase. This is why for phases, for these two phases, okay, only U components of velocity will be considered for the mass flow rate. So if we consider that we have a flow field with a certain velocity profile U that can vary with, that can be function of x, y, z, and time, okay, then we can say that if you consider this phase, we have a certain velocity U, then how to define the mass flow rate that is coming in here? M dot n here can be written as, you know that since it's an elementary phase, I can say dm dot n, so it's very small mass flow rate, equals to rho times the velocity crossing the surface, which is u, times the area. You know that the expression of m dot is rho times velocity times area. Here, what is the area of the phase? You have a phase of area dy times dz. So it's times dy times dz. Okay? So in this way, we can say that the elementary mass flow rate coming in here is rho u dy dz. Okay? Now, what will happen on this phase? If you have a velocity u at this level, you will not have exactly the same velocity here, because you might have u can vary with position. Okay? And as we moved from this point to this one, we are just moving along x. Okay? Because we only move along x, then we can say, you know, from Taylor expansion, okay, that if I have a function f of x, I can write that f of x plus dx can be expressed function of fx by doing Taylor series. And if I just consider the first order term, I can write it that it's equal to fx plus del f by del x times dx. Okay, so if we apply this on rho u, because sometimes rho also can be variable. So if I consider rho u at at section x, at section x plus dx, the value of rho u will be applying Taylor expansion, and we do truncation to the first derivative. We have rho u plus del by del x rho u dx. And then don't forget to multiply by the area, which is the same dy by dz. Okay? We can do the same procedure to define mass flow rates along other directions. So if you consider now along y, you have the v component of velocity, which will cross these surfaces. You have the plane surface here of area dz times dx, and the plane surface here also of area dz by dx. So if we show all mass fluxes on the next slide here, here you have presentation of all mass fluxes, all inlets and all outlets. So now once you have the expression of all your inlets and all your outlets, mass flow rates, you can replace back into conservation of mass. Okay? And conservation of mass states what? States that the variation with time of mass in the control volume. And in this expression, you can replace dv by dx times dy times dz. This is the elementary volume you are considering here, plus sum of m dot out minus sum of m dot n equals to 0. Now you can, if you look at your terms, you can see that you can do many simplifications, and the final result will be as follows. So as we said, using the Taylor theorem, we can use this formula to find the relation between, let's say, u at section x and u at section x plus x. Okay, we can do the same procedure for v and w. Okay, so when we replace now into the conservation of mass, after simplifying terms, you end up with the following. This is what is called conservation of mass for in differential form for a very small control volume. Okay, and this is expressed in Cartesian coordinates. So if you have frame XYZ, we'll see after that we can express a conservation of mass in several frames, in Cartesian, which is XYZ, or in polar coordinates, R delta Z. You also have spherical coordinates, but in this course, we'll limit ourselves to Cartesian coordinates and cylindrical coordinates. Okay? Now, as you can see, they simplified dx, dy, dz because it is common between all of these terms, and we end up with this final relation. Okay? Now, this is valid for compressible and incompressible flows. Now, what will happen if the flow is incompressible? So when we say incompressible flow, this means that rho is constant. Okay? And if rho is constant, then del rho by del t will cancel out. So in case we have incompressible flow, and rho, since rho will be constant, we can take it outside of the derivative for each term, and then taking it into factor, since rho times del u by del x plus del v by del y plus del w by del z is equal to 0, rho can be simplified, and we can say that if we have incompressible flow, this is the continuity equation in differential form. Del u by del x plus del v by del y plus del w by del z equals to 0. Okay? Any question until here? Okay. So now, if I consider the following case, okay, then we can say that this equation can mathematically be written as, so the mathematical operator is divergence of the velocity vector. So in math, we can define the divergence of a velocity vector as grad dot v, dot product velocity. And the grad operator is defined as del by del xi plus del by del yj plus del by del zk. Okay? And then since velocity vector is ui plus vj plus wk, when you do the dot product of the gradient operator with the velocity vector, you will get del u by del x plus del v by del y plus del w by del z. Now we say that the incompressible assumption will hold in case the Mach number square is smaller than 0.1. And what is the Mach number? The Mach number is defined as the flow speed over the sound speed in this fluid. Okay? So even sometimes if you have gases which are compressible, if the Mach number calculated is smaller than 0.1, you can treat them as incompressible flows. Okay? Let us consider a small problem. The velocity component for a certain incompressible steady flow field is given by u equals to x squared plus y squared plus z squared, v equals to xy plus wz plus z, and w is unknown. Okay? We want to determine the form of the z component, the w for the velocity field required to satisfy the continuity equation. So in order to satisfy the continuity equation, the condition to meet is that del u by del x plus del v by del y plus del w by del z equals to 0. So all we have to do here is to apply this formula. We have the expression of u. So when we say del u by del x, this means that we want to calculate the partial derivative of u with respect to x. Del u by del x is equal to 2x. Okay? Now, always remember when you do partial derivative, the other variables are considered as constants. Okay? Now, for del v by del y, v is defined as xy plus yz plus z. So when you derive v with respect to y, x and z are constants. This is why the derivative of xy will be equal to x, and the derivative of yz will be equal to z. So del v by del y is equal to x plus z. Okay? So now, replacing del u by del x and del v by del y by their expressions in the continuity equation, you can get the expression of del w by del z. So del w by del z is minus del u by del x minus del v by del y equals to minus 2x minus x minus z, which give you minus 3x minus z. And now you know that since you have the partial derivative of w with respect to z, you can conclude by integration with respect to z, what is the expression for w. So when you integrate with respect to z, okay, instead of adding a constant, you add a function of the other variables, which are x and y. So here, if you integrate with respect to z, x is considered as constant, so the integral here is minus 3x times z. And here you have variable z, the integral of z is z squared over 2. So w is minus 3xz minus z squared over 2 plus a function of x and y. Now, to determine what is f of x and y, okay, we need to have additional information, and they should give us additional information to determine what is fxy, because we can consider any function of x and y can have any form, and the conservation will of mass will still be satisfied. But we don't have one function of x and y that will satisfy this relation, because the continuity equation will be satisfied for any function f that is only function of x and y. So we have infinity of solutions in this case, okay? And to determine a certain function, then they should give us additional information to completely determine what is W in the case considered, okay? Now, as we said, we can define conservation of mass in several types of frames. We can work in Cartesian coordinates. We can work in polar coordinates. So for example, if you are working in frame r theta z, so r theta z, if you want, is a frame that can replace x, y, z. So z will remain as it is if you want. Z is common between the two. But the difference is that plane xy, instead of defining a point by x and y coordinates, we define it then by the following. This is O. We consider R as the distance from O to the point of interest. So this is OP is equal to R. And theta represents the angle between a certain reference line, which can be x, for example, here, and OP. So this is theta. And then the definition of the point just required to know point location, just required to know R, theta, and Z. Okay, and we can link both coordinate systems because you can look from this figure, you can write that x is equal to R cosine theta and y is equal to R sine theta. Okay, so we can show that the differential form of the continuity equation in cylindrical coordinates is of the following form. Demonstrated, we just need to do the same procedure we did in Cartesian coordinates. So we take a certain control volume and we apply on it continuity. We find the expression of the different mass flow rates. After simplification, we get the following. So the general relation for compressible and incompressible flows is del rho by del T plus 1 over R del of R rho VR by del R plus 1 over R del rho V theta by del theta plus del rho VZ by del Z equals to 0. Okay? Now, in particular, if I have a steady state case, okay, what will happen? Del rho by del T will cancel out. So I will have the remaining term. So for steady compressible flows, this is the relation. When we say compressible, rho is not constant, so I cannot take it outside of the derivative. On the other hand, if the flow is incompressible, so for incompressible flow, what will happen? Rho is constant. So if the flow is steady or not, this term will cancel out because del rho by del T, because rho is constant for any time and any position. So del rho by del T will cancel out, and I can take rho outside of the derivative for all terms and take it into factor. Since the term is equal to 0, rho will cancel out, and I will end up with the case that for incompressible flow, in case of steady and unsteady case, I have the same relation because rho is constant. And the relation is 1 over R del R VR by del R plus 1 over R del V theta by del theta plus del VZ by del Z equals to 0. Okay, so this is the conservation of mass in polar coordinates. Now, which one to use depends on the problem and the type of problem we are dealing with. So when we do problems together, we'll understand in which case I select Cartesian frame, in which case I select cylindrical coordinates. Now, we will define now the stream function. Okay? The stream function is an interesting function because it has a lot of application and fluids. So first, if we consider a steady, incompressible plane, two-dimensional flow, okay, then if we want to write the conservation of mass in the differential form, so when we say 2D flow, this means that we just represent the velocity field by u and v, since the third component will be 0, okay? So we have just a 2D flow. Then the continuity equation will reduce to del u by del x plus del v by del y equals to 0. The third term, del w by del z, will cancel out because w is equal to 0. So in this case, we have two variables u and v that are needed to define our flow. Now, the idea of a stream function is a function that can relate the velocities, okay? And in this way, instead of needing to define two variables, u and v, we just need to know one function to define the velocity. So this is our purpose, to define a certain function that once we know it, we can determine the velocity field. How this is possible? If we consider the following definition, if we define the function psi of x and y in a way that the u component of the velocity field is equal to the partial derivative of psi with respect to y, and the v component of the velocity field is equal to minus del psi by del x, okay? Then why in this case we can simplify the analysis? Because look, first, how we got this definition, why we end up with this definition, because we can make sure together that if we define this function in this way, we will always satisfy the conservation of mass. So if I can find a function psi in a way that u is del psi by del y and v is minus del psi by del x, then I am sure that this represents the velocity field of a 2D flow. Because what is the condition for conservation of mass? The condition is del u by del x plus del v by del y should be 0. So let us try by using this definition and replacing in the continuity equation, we will verify that this will always be satisfied. So if the way to define psi is to consider that u is del psi by del y and v is minus del psi by del x. So if I replace in continuity u by del psi by del y, I will get del by del x, del psi by del y, plus del by del y of v, and v now can be replaced by minus del psi by del x. What do you conclude? You get that the second derivative of psi, the second order derivative of psi with respect to y and x, minus the second derivative of psi with respect to x and y equals to 0. And you know well that if I derive first with respect to y, then with respect to x, or if I do the opposite, I will still obtain the same result. This is why these two terms are equal to each other. So I will always get then that the result is 0. So this means that it is enough to find a function psi in a way that u is del psi by del y and v is minus del psi by del x to get the velocity field. Because once you know psi, then you can find by integration u and v. Okay, so this is the importance of the stream function. So instead of having to solve for a flow field, instead of having to determine two functions u and v, the purpose will just be to determine psi. So if I determine psi, I can determine u and v. Okay. Now, what is the importance of the stream function? We'll see together. It has a lot of applications. So one particular advantage of using the stream function is related to the fact that lines along which psi is constant are streamlines, and we'll demonstrate this together. So if you can find lines where psi is constant, this is equivalent to finding streamlines. And this follows from the definition of the streamline. Okay, if you remember, for the streamline, the slope at any point along the streamline is defined by dy by dx is equal to v over u, where v is the y component of the velocity field and u is the x component of the velocity field. So because we said that streamline is defined in a way that at any point the velocity vector of the flow field is tangent to the streamline. And from here comes the definition that dy by dx, which is the slope of the streamline, is equal to the slope of the velocity vector, which is v over v. Okay? Now, if we want to express the change of value of psi function when we move from a point xy to another point x plus dx, y plus dy, we can write that, you know that when you have a function of several variables and you want to find d of the variable, you should consider the partial derivatives with respect to all variables. So for example here, psi is function of x and y. So d psi is del phi by del x, which is the partial derivative of psi with respect to x dx, plus del psi by del y dy, which is the partial derivative of psi with respect to y times dy. Okay? So now, if we replace, okay, we already know by definition that what is del psi by del x? We defined v as minus del psi by del x. So we can replace del psi by del x by minus v dx. And we can replace del psi by del y by u, because from definition, the stream function psi is defined as in a way that u is del psi by del y and v is minus del psi by del x. So we can say then that to have a change in the value of psi, the change in the value of psi is equal to minus v dx plus u dy. Now, if we want to get the equation of lines characterized by psi constant, then d psi will be equal to 0. And along a line of constant psi, since d psi is 0, then this term also will be 0, which leads to minus v dx plus u dy equals to 0. And if you rearrange terms, you end up with, for constant psi, I have that dy by dx equals to v over u. And this is the definition of streamlines. This is why we say that lines of constant psi correspond to streamlines. Okay? And this is great because streamlines, we know how we can get them experimentally, okay, by observation. So if we do, let's say, if we do smoke visualization, we can see streamlines. So we can experimentally find streamlines equations and then determine psi function. And from psi function, we can deduce the expression of the velocity. Okay. Now, another importance of psi, okay, is that it can be used to calculate the volume flow rate between two streamlines. So if I want to calculate the value of the flow rate between two streamlines, I can use psi. How? For example, if you consider the following flow, you have different streamlines, and we already said that we have demonstrated that for constant values of psi, we can draw the streamlines. So if you consider, for example, two streamlines, streamline 1 corresponding to value psi 1, and streamline 2 corresponding to value psi 2. Okay. And we want to calculate the flow rate between two streamlines. How we can do it? Okay, for example, if you consider a particular line AB, and we want to get the corresponding flow rate crossing this line, okay, we know that to calculate for any cross section, if you want to determine the flow rate, okay, we should consider the component of velocity perpendicular to the section. Okay, so since here the section is vertical, then we only consider the u component of the flow. And along line AB, we can then say that q can be defined as integral from, if this point is characterized by x1, y1, and this point is characterized by coordinates x2, y2, Okay. Then we can say that the flow rate per unit depth, if you want, the flow rate. So here you will get the value in meter square per second, which is a flow rate per unit depth, we say, okay? Because it's meter cube per second over meter, so it's per unit depth. So the flow rate per unit depth here is calculated as integral u times dy. Okay, why? Why we can do this? Because in general, when you want to find the total flow Q over the area, okay, not per unit depth. So if you want here to differentiate both, if you want to say Q over the area, how you define it? You define it as integral U dA, okay? And here we did U only because the section is the area we consider. So if you consider a certain depth B, okay, if you consider a unit depth B, when we say per a unit depth, so you can consider that B equal 1, okay? So if you want, you can consider that for B equal 1 meter, what will be Q in meter cube per second? Or also, you can say if I want to get the value per, just the value per unit length, okay? You can consider that it's like I'm dividing by the depth. So both strategies are true, and I will give you the same result. And you can define the Q as big Q over B. And then the unit of Q will be meter square per second. And the unit of big Q is meter cube per second. And when you consider B just equal to 1, you can consider that you get this big Q here per unit depth. Okay? So you know that dA, the elementary area here will be what? The elementary area is dy times the depth. Okay? So I can replace dA by dy times the depth. Now, if I consider a depth of 1, because we are talking per unit depth, so depth equal to 1. So I replace B by 1. Then I get that the flow rate for a cross section of depth 1 is integral from y1 to y2 of u dy. Okay. Now, if I replace u by its expression of psi, which is del psi by del y, I will get that Q is integral from y1 to y2 of del psi by del y dy. And since I am integrating over AB, AB is characterized by a constant value of x. So x is not varying over AB, only y is varying. And then this is why when y is the only variable, you can consider that del y and dy can simplify. Okay? And therefore, you end up with Q equal to integral between y1 and y2 of d psi. And this means that the flow rate can be given by psi at location 2 at y2, which is psi of streamline 2, because we have seen that the value of psi is constant along the streamline. So it's psi of streamline 2 minus psi of streamline 1. So from here, we know the importance of calculating of the psi function, because it can allow us to calculate the flow rate for per unit depth, for a unit depth between streamlines. Okay, for the same relation can be derived if I want to calculate the flow rate from between B and C. So if you want to calculate the flow rate between B and C, then the only component that will cross this section is the V component. And then I can say that over BC, the Q is integral from x1 to x2 of V dx. And similarly, along BC, okay, y is not varying, so the only variable is x. This is why dx and del x will cancel out. And again, I will obtain the same result because I will get here integral, okay, minus integral between x1 and x2 of del psi, okay. So now you got a negative result because it can be, it depends if it's an inlet or an outlet, okay. So, but at the end you can get the corresponding value of Q by doing psi2 minus psi1, okay. So from here we have demonstrated that the flow rate Q, okay, can be given by psi2 minus psi1, which is the difference between between the two stream functions values, okay. So this is an important application which allow us to find Q between streamlines. And note that because the volume flow between any two streamlines is constant, velocity will be relatively higher wherever the streamline are close together, and relatively low wherever the streamline are far apart. So for example, if you consider, let's say, these streamlines, okay, it's logical that when you have a larger space between the streamline and you want to integrate over it, the velocity, the values of velocity will be lower because at the end, the flow between two streamlines will be constant, okay. So we have that in this case, we got that at different sections, what will happen as the streamlines will be closer to each other, okay, you have the velocity will increase, and this is expected because of conservation of mass. So observing values, observing streamlines will help you into knowing regions of high velocity compared to region of low velocity, okay. Any question on this? So now as we have seen before, we can deal always with two types of coordinate systems. We can deal with Cartesian coordinates, we can deal with polar coordinates, okay. So as we define stream functions in Cartesian coordinates, also we can define them in polar coordinates, and then we'll have the following. We will have that 1 over r del r dr by del r plus 1 over r del v theta by del theta plus del vz by del z equals to 0, okay. So this is the this will give you the equation of a 2D dimensional incompressible flow in r theta plane, okay. And from here you can define the stream function psi in r theta plane in a way that Vr is 1 over r del psi by del theta, and V theta is minus del psi by del r, okay. So if you define psi in this way, then if you replace back into the continuity equation, you will verify it. This is why we say that in polar coordinates, these expressions will allow us to relate psi to the velocity field. So if I know the value of psi function of r and theta, I can deduce Vr and theta, okay. Now we will move to the motion of a fluid particle, okay. So in this chapter, we will consider motion of fluid particle, and we will apply, if you want, like second Newton law, but instead of dealing with solids as you did in dynamics, we will deal with fluids, okay, which will be expressed by the conservation of linear momentum relation. So if we consider the finite element moving and changing shape and orientation, okay, we can have several possibilities of behavior during motion. So we can have severe distortion, we can have infinitesimal particle changing in shape, so it can undergo stretching or shrinking, and we can have rotation of the element sides. So we'll consider the different possible types of behaviors that can face a fluid. We have cases where sides will remain straight, which is a simpler case to consider. So we will divide particle motions types into several parts. We will deal with translation, rotation, linear deformation when we have the particle side stretching or contracting, and angular deformation in case the angles between the sides will change. So we'll consider all of these possibilities for fluid behavior. Now, to start with, we will define the acceleration of a particle in a velocity field. Okay, so if you consider a certain particle moving in a velocity field, we can characterize the velocity of the particle function of the position in the flow field xyz and the time t. Okay, so this is why we say that in a fluid domain we can define the velocity vector function of x, y, z, and t. Okay, if you just consider the particle, the velocity of the particle can be just defined with respect to time. So I track it with time, and at each time t, it will occupy a certain position. Now, this is the Lagrangian approach. Now, when I consider the Eulerian approach, I will consider the velocity function of position and time, because in each position, the velocity can change. So for a fluid domain, I can define 4 variables, x, y, z, and t. And the velocity field will be defined function of these variables. And as you know, the acceleration is defined as the derivative of the velocity. So we will learn here how to do the total derivative in a fluid domain. Okay, so first